Towards the break, computation, decomposition, how do we do this? How do we compute this? What do we compute? How do we perform this overall hypothesis test? I repeat the model here. With that model, what do we mean by that? I mean that there is actually a computation that can tell me how large are the alphas, because that's what I should ask. I should try to find a test statistic that would measure how large are the alphas, how different are each group from the overall average, right? That's a kind of a measure of the size of the alphas. And then I also need, for the statistics here, to have something that can tell me how large are the variabilities, sort of the natural variabilities within the groups, right? Because if I have two groups like this with a lot of variability, then it would be difficult to claim that one group is different from the other group, say. It turns out that we can actually see it like this, that we can compute two things that then together gives the total variability that we actually know from before. So we can decompose the total variability in the data into two sources, into two pots, where one of them tells about how different the groups are. I use groups a lot. The classical original name for the groups would be treatments. So that's a generic name used in ANOVA settings, because originally this was developed for having different treatments, either of different, classically there's a lot of field experiments by Fisher in the UK, in Rothamsted, doing experiments on different crops that got different treatments, and then you want to measure which treatment gave the highest yield. Classical agricultural experiment. Could also be such a clinical experiment that I mentioned the first day we met by the ship doctor back in many few hundred years ago, where you put patients in one group and you treat them by what then is a real medical treatment. But the word treatment is used generically, and sometimes I call them groups just to take me a bit away from this word treatment that might for some have a very specific meaning. But here it's used very generically to talk about the different groups or treatments. So that's why the generic abbreviation TR is used for treatment. The reason why we call this for now, and you've seen next time we will go beyond this, we talk about, funny enough, one-way analysis of variance. It's still multi-group, but only one way. So there's only one table, or only a one-way table of a number of groups, right? It could be a two-way table of data, as we'll get back to. I've mentioned it already. Could be a two-way. There could be two groups. There could actually be a multi-way table of, could be A by B by C. So this is just the start even to expand this idea any further. Today, we just talk about one way. So there is only one factor, one way of the table in play today. And the last point, I've said that already. The funny name is due to the procedure that you will see now. The procedure to compare means involves certain variabilities. Here is something that you already know. I have my data set, right? 12 numbers in the toy data, right? 444. So I could just see it, and in my data set I would typically have it stored just as 12 numbers in a column, because I would have the group information stored next to it in another column, right? So in a way I could just treat it like I was taught in my first day at this course, and then I could say, hey, let me compute the variance of these 12 observations to see how much are they varying, right? That's what I started to do here, right? Now I double index the numbers, but there are still just 12 of them, even though I call them 1, 1, 1, 2, 2, 1, 2. I call them with these double index but there's just 12 of these numbers here. So the sum here, when I sum up over everything, I have to do a double summation and this to be this is the double summation sign to tell me I'm summing up something from all the 12 observations here. And what am I summing up? I'm summing up each observation's difference to the mean of everything. Yeah, that's a step towards computing the variance. When I square them and I add the 12 numbers up, if I divide it by 11 here, I would have the sample variance of those 12 numbers, right? This we call the total variance, the total variability. It's a slightly imprecise name, but having defined what it is, we should be all set, right? Because it's not really a variance, because I don't divide by anything, but it's the core of a variance computation, right? It's a kind of the sum of everything. Then we could also study residuals, like we've done a number of times. What should residual be in this case? Residuals would be to take, again, each individual number, but now comparing the number with the mean of the group, right? So, anyway, I could do it here maybe. I have mean of group 1, mean of group 2, mean of group 3. I have individual data points, right? And then this number is comparing these small green ones, right? That's the thing here. I'm taking each observation and comparing with, so it's a measure of the fluctuations within the group, right? But taking out, that's a way to say it, removing the group differences in this approach here. Well, if we should visualize the other one, what would that be up here? If it's the same data set, let me visualize that. Then somehow I have the overall mean here somewhere, right? And the different ones here would be to take each individual observation and compare with the overall mean. That's the total variability, right? That's a larger number in this case, because compared to the overall mean, this variability is larger. It's a total variability. Whereas the residual variability would typically be smaller, exactly when you model something by a regression line. But we're not having a regression line. And then finally, maybe the most interesting thing, maybe, namely the one that actually tells us how different, let's use the same colors, how different are you have the overall mean, how different are the means, the individual means from the overall mean, right? I'm looking at how different are the individual means to the overall mean. This is the core number, right? This is the number that measures how different are the three groups. This is kind of a variability also, because the way that I measure group differences, when I have more than two groups, when I had only two a few weeks ago, I would just compare them directly. One average with the other average, subtract it, and then do stats on that number. Because with only two, it's obvious I can just compare the two, right? When I have three and more, what is the single number that should tell me how different are those groups? Well, that's a variability like that, right? It's comparing each of the groups to the mean of everything. So that would be a single number telling me how different are the groups from each other. What is the group-to-group variability? What is the between groups variability? 3 words, sentences for the same thing. That's why it's called analysis of variance, because this is a variability. So we use a variability to measure the difference between means, right? So that's where the name comes from. When you start thinking about it, I at least a few years ago adjusted, and finally I accepted it makes sense somehow to talk about analysis of variance, even though the means are in focus. So that's why. Technically, you're doing it across the 3 groups. So the K would be 3 in my toy example. The K would be 12 in the Bang & Olufsen example, right? So I take those 12 numbers and then I multiply them. Actually, it's a double sum. There is also an inner sum from J to Ni. And Ni could be different, but since it doesn't depend on the J, this inner sum, J to Ni, becomes just Ni, the number of observations within each group. Somehow it makes also good sense that when I measure group differences, somehow you could see the groups, if they came with different numbers, if I had 100 numbers in one patient group and just 10 patients in another group, when I then measure this, eventually I would end up giving higher weight to the average, to the group with the 100 than to the group with 10. And even though this is not a proof of anything, somehow it makes sense also, I think, that kind of effect is coming in. Then we collect all these computations. So here's the thing for you. These are the defining formulas, right? And I jump one slide back again here. These 3 defining formulas for the total variance, the between group variance called SSTR, and the within group variance called the residual variance, 2 of them add up. The between and the within, they add up to the total. That can be easily proved mathematically if you can do the square of 2, what's that in English? Kvadratet på en toledig størrelse. When you square 2 things. What's the English name for this little rule? Hey, come on, guys. That's for 3rd grade. Why the hell don't you remember then, you stupid professor? We collect all these computations in a table. And when I say we, it's basically everyone who implemented these tools in any kind of software out there. Decided, due to what the historical way this was coming out, we collect these numbers and some more that goes with it in the so-called analysis of variance table, the ANOVA table. There is even a function in R. There are actually several functions. Here's one of them, which has the name ANOVA. And if you use ANOVA on the output of such a linear model call that I showed you, where you take Y to be described by treatments, where treatment is a factor, is a grouping factor, then R will spit out a table like this, which in a more friendly or formal way is the table that I've put above. Basically, the starting point of this table are the 3 so-called sums of squares, because each of those are summing up squares, the square of things, right? So that's the generic name of these different variabilities, because they're not really variabilities, because so far we haven't divided by anything. We call them sums of squares. Then it turns out that, of course, we need to divide by something when we are coming at the final thing that we'd like to do. The F statistics that I didn't actually show you until now, the F statistics, and actually I think I will postpone that because I have it on the list, but you can see it here already. We collect this. Let me just for now say that the table would also give us degrees of freedom. Look at that, degrees of freedom. I've discussed that with various people. It's a way degrees of freedom is used in different ways. It's a name for the dimension of whatever I'm looking at somehow. So when I'm looking at the treatment, the sums of squares for treatment, I have, in this case, I've used k numbers to compute that variability for the treatments, right? So that corresponds to actually computing a variance based on the k means, k different means, k being either 3 or 12 in the two examples I've shown you. This means that this is a variability from group to group, and it turns out that the right way to average such a variability of k pieces of such k squares is to divide it by, and that's what I do here, I divide it by k minus 1, and I call the k minus 1 for the toy data 2, the degrees of freedom for the groups, for the treatments. Now when I compute the residual mean squares, as it's called, I call them not sums of squares, but I call them mean squares when I divide, when I mean them, when I average them with the right degrees of freedom, with the right number. So when I'm averaging the residual sum of squares, the one that measures the fluctuation within group, we are going to use n minus k. Not n minus 1, not n minus 2, but n minus k. You can see the analogy, I hope. So that's n minus k, 12 observations minus 3 groups, that gives us 9. So that's the way to compute the average within group variance, by dividing the sum of squares for residuals by 9. Here's a little toy example, which is, I know, very difficult to read, but let's just spend a couple of minutes and then jump into R and see what the result is. It's just to let you know, actually again, I have given you the defining formulas for these sums of squares. I expect you to know these formulas. I expect you to be able to use those formulas. I expect you to understand what is inside these formulas. In the old days, you would then have been given a number of hand calculation formula that makes life a little bit easy if you were to do hand calculations yourself. But we are skipping those now because we're never in real life going to do hand calculations, of course, or old-fashioned pocket calculator things. If you're still doing that, throw it in the bin. I'm sorry, but maybe you have other professors that tells you otherwise. I don't know. I haven't used a pocket calculator for 20 years or something. Maybe when I need to help some of my daughters do it, but then we fight about that. But anyway, as soon as possible, the pocket calculator should be thrown in the bin, or one Friday evening you put it on the floor and you jump on it or something and have fun about that, right? Don't quote me. Oh, I was recorded. Well, bugger. Now I have another problem. Point 3 on the list for being kicked out of this place soon. Let's have a look here. I am trying here to make a little toy example to give you two different cases. We'll look at the cases, and then I do. Here I then do the total sum of squares and the residual sum of squares by hand calculation or explicit use of the formulas I gave you. So this is kind of my definition of manual computations, right? That I use the formulas. You can even see them put into a function there. I use the explicit defining formulas that I gave you, and I implemented those by sort of basic R stuff. And also, this is just for illustration purposes, because the LM and the ANOVA function will do all this for us in a real life setting, right? But I'm challenging you in this course. In your later life, I don't care. You can just use the LM and ANOVA and everything. But in this course, I want you to be able to do both. It's not going to be too easy on you. You should be able to be up and practically working like you're in the business. You should learn that. You're an engineer. But I also want you to understand what's behind it, right? And why? Well, the same answer. You're going to be engineers. Engineers know what they do. Some of them. Have I ever told you I'm not an engineer? I'm trying to be. Let's see. Actually, here also you can see some hand calculation formulas. Here comes the example that I have had on the slide. 10 observations in each group, 3 groups. I'm constructing 2 different data sets. And here they come. Here they were supposed to come. I have some hidden things in this. I'm just going to close down. I think the explanation is that when we sometimes jump between different systems, Unix-based, DOS systems, Windows systems, we tend to have some ASCII coding problems sometimes. I think that's what's hitting me. Or my computer's just getting tired. I think actually I will not waste your minutes with this, and then I will instead say fine with that, and then we can show it later, and then I'll make sure to have this 4th point ready for you before the break. That